Eric Rexted, University of St. Andrews, with the introduction to the second exercise in the unit on distance sampling analysis using R. This analysis or exercise is based around the amakihi dataset that was published, that was described in a paper published by Tiago Marsh and his associates in 2007, and the analysis reappears in Buckland et al. 2015 Distance Sampling Methods and Applications book as one of the case studies. We repeat it here because although this analysis was originally done in Distance for Windows, it can also be done in R. However, there are some data manipulations associated with it that we describe here, and it also serves as a useful test case for doing analysis from a candidate model set, a rich candidate model set. So with that introduction, there's a picture of our study animal. We'll be looking at some plotting skills that come in useful, that come in handy both for the exploratory data analysis phase of the work, as well as the understanding of the fitted detection function. So the data set here actually lives on the website associated with the Buckland et al. 2015 book. So you can download it from that location and put it on your own computer, or you can ask the read CSV function to read that file directly off of the web address. Either way, once you get the data into R, you should have a look at it and notice that there are the usual things associated with the data: study area, strata, labels, point transect identifiers, the amount of survey effort associated with each one of those point transects, and in this case it should be radial distance rather than perpendicular distance because it is distance sampling data. But in addition, we have some extra fields: the initials of the observer who made the detection, and something about the detections themselves, the time that the detection was made, measured either in hours after sunrise or minutes after sunrise. One thing to note is, in contrast to the duck nest data, there's no area measurement field in the dataset. So we don't know the size of the study area from which these data were collected. That's not going to cause us any difficulties because we're not really interested in this exercise in estimating density or abundance. We're simply going to be fitting and contrasting various detection functions. So off we go. There's a couple of missing distances here, and so we're going to toss those out of the data set using this command. And then we can start having a play with the data themselves. And so I have a question over here in the margin that says, let's build some histograms and such like. And we can make some box plots of our data. And there's some information here. There's some examples of how would you go about writing R code to start looking at the distribution of these radial distances, and in particular how those distributions of radial detection distances might vary across observers or might vary across hours or minutes after sunrise. Those are some plausible questions that an analyst of these data might ask themselves to say, is there an effect on detectability of different observers or of time since sunrise? And so we give you some hints about how you might go about investigating these observer-specific or time-specific differences in detectability. And after doing some visualization or some inspection of the data, you can then make an assessment as to whether you ought to accommodate those changes or that variability in detectability in the detection functions themselves. So where this all leads us is that we are going to include covariates in our detection functions. But adding covariates to the detection functions can sometimes be a useful thing to do, but recognize that it is going to make the job that you ask the detection function fitting to perform more difficult. One of those difficulties can arise when there's a strong correlation between the predictors that we place into our model. Remember, we're trying to predict detectability as a function of distance and other covariates. If other covariates that we include in our model are highly correlated, we have a situation called collinearity. And that collinearity can create difficulties for software in fitting those types of models to data. So I ask you over here in the marginalia to think about looking at potential collinearity between something called minutes after sunrise and hours after sunrise. Another challenge when fitting detection functions with covariates is that sometimes the covariates might be measured on highly different scales. In other words, minutes after sunrise can take on values between 0 and 300 or 400, whereas observer or hours after sunrise can only take on values between 0 and 4. And so having covariates on widely different scales can again introduce difficulties in the actual fitting, the parameter estimation associated with fitting detection functions. And so there's some effort expended here in section 6 of this exercise to adjust the data of the covariates so that the fitting exercise can be done more smoothly. And so there's the conversion of hours after sunrise to a factor covariate. There's a changing of the levels of these factor covariates. You can read about that. It's done to make the results that we get in R consistent with the results that Distance for Windows produces. The continuous covariate, minutes after sunrise, as I said, is measured on a very different scale than the other covariates. And so a way to bring minutes after sunrise into a comparable scale is to standardize the data. So we're going to take each minute after sunrise measurement and divide it by the standard deviation of minutes after sunrise. And you can look to see whether that tidies up the scale, the range of values of minutes after sunrise. Once we've done all of that tidying up of the data, we're actually ready to think about what our candidate model set is. what models do we wish to fit to the field data. Once we've identified our candidate model sets, we can then make many calls. We'll make one call to the DS function for each of our candidate models. And so off we go now, doing what we did in exercise 1, repeatedly calling the function ds. Note the distinction between exercise 1 and this exercise in that exercise 1 was with line transect duck nest data. This is point transect bird data, and so we need to tell ds that we're fitting point transect data. Otherwise, we still have our key functions and our adjustment terms. I've introduced a new argument to the ds function, namely the truncation distance. We're going to truncate our data, or we're going to truncate these point transect data consistent with the way in which Marsh et al. 2007 analyzed the same data set. So off we go, following the questions that are here in the margin, fitting many different detection functions from our candidate model set. Once we've fitted many different models to our data, we end up with many model objects. We'd like to be able to summarize all of those model objects together to come to some sort of a conclusion about the most appropriate of those candidate models for the data that we've presented it. There's a very useful function in the distance package called summarize DS models, in which we simply specify all of the candidate models that we want compared, and this summarize DS models will do a nice job of presenting a very concise summary. At that point, we'll probably do some model selection work, and we can then start to contrast the shapes of the various detection functions fitted to these data. So here's the model without any covariates. Here's the model with observer as a covariate. Here is, I won't tip my hand too much, but the best model. And you can get a look at the various shapes and the manifestations of the effect of the various covariates on the detection function. Here's some literature. This is the original paper upon that was in which these data were first analyzed. So good luck. Enjoy analyzing these amakihi data.